right, let's look at the bottom part of the theorem called anti-differentiation of a composite function. It says, if u equals g of x, have we ever seen something about let u equal whatever? Have we ever seen something like that before? Chain rule, right? If u equals g of x, then du would be, then you'd have to chain rule that. That's a function of x, so its derivative would be g prime of x times the derivative of x. All right, you're kind of chain ruling something you don't need to, but derivative of g of x times the derivative of x. So then, that means that the antiderivative, that notation of an indefinite integral means antiderivative of f of u. So the indefinite integral of f of u du would be capital F of u plus c. Now you probably say, well, that's exactly what we had before, just with an x instead of a u, and you would be exactly right. But the fact that that's a u is actually a kind of a big deal, because what is u? It's a function itself. It's an equation. It's a function. Okay? So this part right here that I just kind of glossed over, that g prime of x dx, that's important. That du right there has to be the same thing as g prime of x dx. If I were you, I would be sitting there right now going, I don't know what he's talking about. Okay, good. That's okay. All right, not good, but that's okay.
That is correct.
Now, let's back up a little bit, because remember, that was the second part of the theorem, or not even the second part, but that's the bottom part of the theorem. Let's go back up to the top. G is a function whose range is in an interval, and f is a function that's continuous on that same interval. G is differentiable throughout that interval, and capital F is an antiderivative of little f throughout that interval. What? All right, we've got a function f. F is a function of g. G itself is a function of x. So we have a composite function. We have f of g of x. Okay? That's what's going on. We have a function g that's a function of x, and f is a function of that. So that's a composite function. Now, as long as g is differentiable, then we can make this work. Okay? So we've said that the integral of f of g of x, so the integral of this, the antiderivative of that composite function. And then look, instead of a dx, they've got this convoluted g prime of x dx there, instead of just a dx like we had before, because before, were we dealing with composite functions? So with a composite function, it's more complicated. That antiderivative is the antiderivative of f, not of x, of g of x. And then plus c, like we always do on an indefinite integral. Okay? Now, that's a lot of notation. Okay? So that's why this second part exists. Replace the g of x with u, and then since u is a function of x, let's see, how can I, if we have, I'm going to mess up the notation. Let me think for a minute. The derivative of f with respect to x is going to be, am I doing this right? The derivative of f with respect to u times the derivative of u with respect to x. Okay, that's right. I just had an f instead of a y like we always had before. So du Oh, no, I'm going to mess that up. Pretend that never happened. It was correct, it just wasn't helpful. Okay? And so I'm trying to explain to you why the du has to be g prime of x dx, and I'm drawing a blank on how to explain it. Well, because it is what it is, but it's from the chain rule, and all of a sudden I'm drawing a blank on why that's from the chain rule. Yes. Is that all I need to say? Is that's the chain rule? And that's what I'm going to say, because that's the chain rule. Okay? Because the chain, like over here, normally we have, that'd be a U. Try not to let the different letters of the notation get in the way. But that's the chain rule, right? Well, that's that, that, just with different letters in different places. Okay? So, that's not the eraser. All of this still should be fairly confusing. The point is, 2 points. One, there's a theorem that lets us take the antiderivative of a composite function. 2, it's complicated to make it work. Okay? Because we have to have our integrand has to be that composite function times that for us to be able to take its indefinite integral. That doesn't occur all that often in nature. Okay? We're going to have to make that work, especially for a while. We will have to the book author had to carefully make up the problems so that they would work out that way. All right? Just bear with me. All right, now, note, the theorem doesn't tell you how to distinguish between that and that. In other words, the theorem doesn't tell you how to decide what's the F, what's the G, what's the G prime. We have to figure that out, and I will show you how to figure that out. Study tip. There are several techniques for applying substitution, each differing slightly from the others. However, you should remember that the goal is the same with every technique. You are trying to find an antiderivative of the integrand. We will get so caught up in kind of the X's and O's, to use a sports analogy, that we may actually forget what we're trying to do. What we're trying to do is pretty simple. We're trying to find the antiderivative. We're just going to have some fairly complicated ways of coming up with that. Okay? Now, I say we're going to have some fairly complicated ways. Some plays in a sport, I don't know, basketball, you draw the X's and O's up there, and it looks really complicated. Other plays in basketball involve one guy throwing it to another guy who dunks it. So some plays are complicated, some plays are simple. Some of these techniques are complicated, some of these techniques are simple. Okay? Yep. Well, no, not up twice, just up on a very complicated function. It still works like this. You'll still see that kind of notation where little f is the derivative of capital F and f prime is the derivative of little f, or, like, we don't always use that. But if we're going down, if I write it this way, if we're moving down, we're taking derivatives. If we're moving up, we're taking antiderivatives. So we're going to move up. Joseph. Yeah, we've done that. That's the second fundamental theorem of calculus. All right. So we've got this complicated looking thing here, right? We're finding the antiderivative of f of g of x times g prime of x dx, which can be thought of as the antiderivative of f of u du, which ends up equaling capital F as a function of u plus c. Ends up being the antiderivative of that one as a function of g of x, right? U is g of x plus c. Now, this is called change in variables, or change of variables. It's called substitution. It's called substitution by change of variables. So be familiar with either term, change of variables, substitution. Sometimes you even just say U substitution, like the letter U. So substitution and integration is like the chain rule and differentiation. They both involve composite functions. And at their simplest, most obvious, it will be some sort of expression inside of parentheses with an exponent on it. That's again, I don't know if that's the simplest or just the most obvious thing we'll see. So here's what's going on. We're given this, and we're supposed to integrate it. So we say, well, let u equal g of x. So in other words, whatever f is a function of becomes u. So let u equal g of x. Then we take the derivative of that g of x, and we can call that, notation-wise, we can call that g prime of x, right? So if I called the derivative of u du dx, and I call so the left side, the derivative of the left side, I'm calling du dx. The derivative of the right side, notation-wise, I'm calling g prime of x. Now, here's a little algebra trick. It doesn't really work this way. You can't really take a notation and multiply both sides by half of a notation. But the calculus works out the same way as the algebra here. If I multiplied by dx both sides, those dx's divide out, calling that du equals g prime of x dx. So this is one advantage Leibniz has. His notation works out nicely, okay? So that right there, we're going to do tons of that. Tons, tons, tons. Millions and billions of problems like that. So we've now turned this into, look what you do. All of that can now be called f of u. And then look, here's the part that you got to really see. All of this, look what it's equal to. It's now called du. So, using the letter u instead of some expression with x in there now, if that's something we know how to integrate, we're good. We can. If it's not something we know how to integrate, well, then we wasted our time. So part of the issue we're going to have is being able to rewrite our original integrand into a form we know how to integrate. Once we're so then we know how to find the antiderivative of little f. We call it capital F. We put a plus c. Now, at this point, our answer has a bunch of u's in it and no x's. And I'll show you how to put the answer back in terms of x. All right. You know how we've used the power rule for integration? Add 1 to the exponent, divide the coefficient by the new exponent. That works even if it's a u instead of an x. What would u be? U would be some expression of x. So the general power rule, didn't we call one version of the chain rule when we were taking derivatives the general power rule? Yes, we did. So now as we're taking antiderivatives, one version of the change of variables or of the substitution will be called the general power rule for antidifferentiation, or the general power rule for indefinite integrals. And that's where we're going to stop.